So these are some of the things you need to know about different alcohols. Isopropanol is it's a gasoline additive. So things you need to know. Anyways, let's talk about the physical properties of alcohols. The OH of an alcohol can have a big effect on the physical properties, and that's because it can exhibit hydrogen bonding. That is evidenced in the significantly higher boiling point that ethanol possesses over chloroethane that exhibits only dipole-dipole interactions, while ethane has London dispersion. But ethanol, of course, has both, it has the hydrogen bonding, the dipole-dipole interactions, as well as the London dispersion. And so the hydrogen bonding, as you can see, gives a significantly higher boiling point than the chloroethane. Because it can bond, hydroxyl groups can attract water molecules strongly. So generally, alcohols with small carbon chains are miscible in water, right? And that's because they have a hydrophilic region which interacts favorably with water, and a very short hydrophobic water-repelling region. However, as the water-repelling or hydrophobic region begins to get bigger or longer, then they don't readily mix with water, right? And that's what has been observed. Because we know that the hydrophobic groups will repel water. So why are molecules with large hydrophobic groups generally soluble in water? Like dissolve likes, we know that. See, like dissolve like. So alcohols with 3 or less carbons are generally water miscible, while alcohols with more than 3 carbons are not miscible, right? And their solubility tends to decrease as the size of the hydrophobic group increases. Now, an alcohol's potency as an antibacterial agent depends on the size of the hydrophobic group. And the reason is because to kill the bacteria, some of it should, the alcohol should have some water solubility, and also must also have some hydrophobic region, because it will need to be able to penetrate the walls of the bacteria to be able to effect destruction of the bacteria, and so it needs to have a fat soluble or hydrophobic region. So you can see, look at this example. It's an example of a great antibacterial agent, which is hexyl rosuccinol. It has a long hydrophobic chain, right? And this is it has a hydrophilic. This is the hydrophilic. See, so the hydrophobic chain is able to penetrate the walls of the bacteria, right? And while with the hydrophilic chain, it's able to be water soluble. So a combination of the hydrophobic and the hydrophilic regions makes it an effective antibacterial or as well as an antifungal agent. Let's talk about the acidity of alcohols and phenols. Of course, we've looked at the different factors that control acidity: the atom, resonance, induction, and orbitals. And we say the more stable the conjugate base, the more acidic the corresponding acid will be. So if we look at this reaction, we can see that a strong base is really necessary to deprotonate an alcohol, and that's because the alcohol is a weak acid. It's a weak acid. It has a pK of about 18. You see, so you need a strong base to deprotonate the hydrogen, the alcohol. A preferred choice to create an alcohol is to treat the alcohol with sodium or potassium or lithium metal, in which case you would generate the metal hydride and the formation of the alkoxide, the lithium alkoxide. And then the metal hydride will in turn react with another unit of the alcohol to yield the lithium alkoxide and the evolution of hydrogen gas. And so if you add both together, you get the overall reaction. So that's a great way of converting an alcohol to the corresponding base by using either sodium, potassium, or lithium metal. Now, we've talked about area. It's used to qualitatively assess the strength of an acid. And don't forget, the A applies to the atom. In this case, if you can see, you have increasing acidity, pK of 45 to 50. You see, look at alcohols, pKa of between 15 and 18. You see, so I want you to be comfortable with this, and also the pK of amines between 30 and 35 and 40, while the pK of alkanes between 45 and 50, while the pKa of hydrogen halides between -10 and 3. So just get used to some of this. Now we can see here that phenol is 100 million times more acidic than cyclohexanol, because phenol, of course, the conjugate base is stabilized by resonance, while the conjugate base of cyclohexanol is not stabilized by resonance. Can only be stabilized by the atom. You see, and that gives significant stability to the conjugate base for the phenoxide, making it 100 million times more acidic than cyclohexanol. Okay, and that's what we. So, given the relatively low pKa of phenols, will sodium hydroxide be strong enough base to deprotonate the phenol? Of course, it will be, because you are generating a weaker acid. When the hydroxide reacts with phenol, it produces a weaker acid, which is water. And we learned in Chem12 that the reaction always favors the weaker acid, or the weaker base. Now let's apply these factors to alcohols and phenols. We also know about induction. You can see that if you consider the conjugate base of the ethanol and versus the conjugate base of the trichloroethanol, right, you will see that this is stabilized by induction. See, while this is not, right? Why this is not stabilized by induction. As a result, the trichloroethanol is way more acidic than the ethanol itself. Orbital, what type of orbital do the alkoxide electrons exist? Of course, they exist in an sp3 hybrid orbital. Now, solvation is also an important factor that affects acidity. Water is generally used as a solvent when measuring the pKa values. So if you say which of the alcohols below is stronger, to be able to determine the stronger alcohol, we need to consider the conjugate base. By the way, the pKa of alcohol is 16, not 18, while the pKa of tertiary butanol is 18. To be able to consider which will be stronger, you need to look at the conjugate base that forms, and you will see that this is going to be more easily stabilized by solvation, while this will not be. And so, because this cannot be stabilized by solvation, we expect that this will be a stronger acid. We can't use area here. Area is not really something to be used here, and this is what I'm trying to explain. If you look at the alkoxide here and tertiary butoxide, you can see that this is less stable due to the inaccessibility of the negative charge by the solvent molecules due to the steric bulk of the butoxide. So there's a significant steric bulk here, making it impossible for the solvents to stabilize the negative charge. But here you can see that there is a better accessibility because there is lack of a steric bulk there. So that's why the alkoxide is way more stable than the tertiary butoxide. Now, say if we have to use area and solvation to rank the following molecules, if you look at this, if we consider the conjugate base here, you can see that the conjugate base here will be stabilized by the atom and induction. Here is only the atom. Here this can be stabilized by both the atom and resonance, while here this can only be stabilized by the atom. In fact, the fact that the negative charge is not easily accessible is going to be a problem, you see. And that's why you see this is the number 1. That's number 1 because of atom and resonance. This is number 2 because of atom and induction. This is number 3 because it has only the atom, while this is number 4 because even though the negative charge will be on the oxygen, but because you have these bulky groups, the steric bulk will prevent the stabilization of the negative charge, and so this will be the least acidic out of the 4. Now, when considering preparation of alcohols, we saw in chapter 7 that substitution reactions can yield alcohols. And remember, you can use a water, right, or an OH group, an hydroxide, right? And we saw that the substitutions can occur either through an SN1 or SN2. Then you have a primary, it will go SN2. If you have a tertiary, it will go SN1. It will go SN1. So you have, this will go SN1, and it will also give you some elimination product, right? And the SN1 process generally uses a weak nucleophile like water, which makes the process relatively slow. Because if you try to use a strong electrophile like OH minus, you are going to get an E2 reaction. It's going to go E2. It's going to go an E2 route, and you're going to begin to get something like that, see, which you don't want. Okay, and we learned how to make alcohols in chapter 9. You can make alcohols by the addition of water to an alkene, and it could be catalyzed by acid, which is case it's an acid catalyzed hydration, or it could be catalyzed by an oxymercuration demercuration, or you could carry out a hydroboration oxidation. Recall that the acid catalyzed hydration proceeds through a carbocation intermediate, and as a result it's prone to rearrangement. And to avoid rearrangement, all you need to do is use the oxymercuration demercuration. Okay, oxymercuration demercuration. So anyways, that's basically all for preparation of alcohols. These are things that you need to know. It can either be prepared by acid catalyzed hydration to an alkene, or the oxymercuration demercuration, or the hydroboration oxidation.